This call is now being recorded.
Okay, we'll continue with the class. Am I audible to everyone? Yes? Am I audible? Okay. Shall start the class then. Okay, in the last class we discussed mechanisms that are used for providing freshness to see that any message is recently received. That means it is not replayed, right? So the three mechanisms under this, wherein we discussed clock-based mechanism in the last class. Today we'll discuss the next two mechanisms, that is sequence numbers and N1 based mechanisms. So in clock-based mechanism, you know that along with the message, timestamp will be sent from one user to another user. So if the timestamp is the recent time, then that message will be treated as a fresh message, right? And so this is an example which I've considered, right? So with respect to implementation of this method, we can see the four problems, that is existence of clock, synchronization, communication delays, and integrity of clock-based data. Just a minute. Okay, existence of clock, synchronization, communication delays, and integrity of clock-based data. These are the four implementation problems we discussed in the last class. We shall move to the next method or the mechanism, that is sequence numbers. As in the previous method, a clock is maintained at the both the users who are involved in the communication, right? So in this method, actually, logical time should be maintained between the users. That means the order in which messages or the session occur between the communication parties. Okay, so logical time is what? This is nothing but maintaining the order in which messages or sessions occur. So how to maintain this order? By following a counter or a sequence number. You can see an example here. Consider this example where Alice and Bob are the parties involved in the communication. So Alice will send a message to Bob. Okay, along with this message, one second. See, along with this message, the sequence number is also sent from Alice to Bob. Okay, you can see this example here. Transaction ID 43542 is a sequence number, and this transfer 30 euros to account this. This is a message. So along with the message, the sequence number should be sent from one user to another user. Looking at this transaction ID, the other person, that means who receives the message, will find out whether it is a fresh message or a recorded and replay message. Okay, if the sequence number is a recent one, then the Bob will receive the message, or else he will reject the message. So as I said, a counter or a sequence number is followed. Fine. Let's consider this example. Say here, you can see in this image, Alice and Bob regularly communicate with each other, okay, with one another, and wish to ensure that messages they exchange are fresh. So whatever message Alice sends to Bob, those messages should be fresh. That should be ensured, right? So to do this, two sequence numbers are used. You can see here, these are the sequence numbers used, NAB and NBA. Okay, so these are the two counters followed, you can see sequence numbers used to ensure the freshness of the message. So NAB is used, sequence number is used as a counter for the message that Alice sends to Bob. AB, response Alice sends to Bob. Whereas NBA, Bob receives the message from Alice. So these two sequence numbers are used to ensure the freshness of the message that is exchanged between Alice and Bob. Okay, we'll see how it is implemented. See, when Alice sends a message to Bob, that means what? The sequence number is sent along with the message. So this sequence number is nothing but NAB. Okay. So NAB, consider this is a variable for which the number is updated as and when messages are exchanged between the parties. Okay. So to do this, Alice, what she'll do, she has to maintain a database here. She has to maintain a database where the sequence values are stored. Okay. So when Alice sends a message to Bob, Alice looks up her database to find the latest value of the sequence number. Okay, that is NAB. So for example, you can treat NAB value as T new. Okay, that is value, the recent value. Okay, so next thing, Alice sends her message to Bob along with this latest sequence number, that is T new. Now, once the message is sent from Alice to Bob, what Alice will do? She will increment the sequence number NAB by 1. That means what? NAB is equal to T new plus 1. So the sequence number should be updated to the recent value. That is by adding 1 to the T new value. Okay, and she will store that value in her database so that the incremented value can be used for the next message which she wants to send it to Bob. Okay, in this way, what freshness of the messages will be achieved. Fine. So next we'll see what happens at the Bob end. See, whatever the message is, or the Bob receives the message from Alice. What happens here? Bob compares the sequence number. I mean, along with the message, he will receive sequence number, right? That is T new, sent by the Alice with the most recent value of the sequence number. That is NAB, right? So that is sent from the Alice to the Bob. Next, if T new, I mean the new sequence number received at the Bob, if it is greater than the T old, that means T old, this sequence number will be at the Bob end, okay, for the previously received message. If the sequence number of the previously received message, okay, if it is lesser than the T new value, then Bob will accept the latest message as fresh, okay, and then he will update his stored value NAB from T old to T new. Okay, T old to T new. Once it is updated, then he will treat it as fresh message, right? So if the T new, that is the sequence number received at the Bob from the Alice, if it is lesser than or equal to T old, then obviously Bob rejects that message, thinking that it is a old message, or you can say it is not a fresh message. Okay. So this is how the sequence number mechanism works to provide freshness for the message. Okay. So there is an alternative technique with respect to this message where you can see here a unique ID number is used for each new message. A unique ID number is used for each message. Okay. So whenever Alice sends a message to Bob, she will send an ID for each and every message. Whereas in the sequence number, in the previous method, whatever I explained, where each number will be incremented by 1, right? Incremented by 1, and then that value will be stored at the Alice database. Whereas in this method, what happens? An unique ID number will be assigned or associated with each message that Alice wants to send it to Bob. Okay. So here what happens? Bob have to maintain a database consisted of all the previous identification numbers sent. So if n number of messages are exchanged between Alice and Bob, then what happens at the Bob end? He has to maintain the database where all the ID numbers of previously received messages should be stored. Okay. So then he has to make a search with this database whenever he receives from the Alice, right? So he has to make a search in the database where ID numbers are stored for the previously received message. If the duplicate value exists in the in his database, then he will treat that message as a old message. If the number received along with the message is the new one, that means if that number is not present in the database, then he will treat that message as a fresh message. Okay. So if this method is followed, then obviously he has to perform a search operation, right? And also he has to maintain the database of complete ID numbers. So it is inefficient in terms of time as well as storage space. That is one disadvantage with this method. So next, similarly, whatever the problems that we find in the previous method, in this mechanism also we are going to address those problems. Existence of clocks, the first implementation problem that we discussed in the previous method, right? So here you can see clocks are not required at Bob and Alice end, right? So the previously faced problem in the previous mechanism, whatever the first problem we faced, that can be solved using the sequence number mechanism. Next problem is that synchronization, right? So in the previous method, synchronization of clocks that is maintained at Alice and Bob should be maintained, right? So here, in order to stay synchronized, communicating parties need to maintain the database of the latest sequence number. Since numbers are involved here, both the parties should maintain the database of the latest sequence numbers, and that should be synchronized. Okay, and that means, to say the database should be up to date. Next problem that we discussed was communication delay, right? So this, communication delay only apply if messages are sent so frequently that there is a chance that two messages arrive at the destination in the reverse order to which they were sent, right? See, if n number of messages are exchanged between communication parties, then if the order is missed, that means if third message is received first and first message received at third place, then obviously this may happen because of communication delay, right? So here Bob might choose, the receiver end, Bob might choose to accept the message as fresh, not just if n new, that is, sorry, t new, that is greater than the t old, but also if t new was equal to t old, since there is a chance that previous message from the Alice to Bob has not yet arrived. See, if there is a communication delay in this method also, the Bob may receive t new is equal to t old as well. That is what I mean to say. Actually, this may not happen in this scenario, but here the main concern is that the messages should be fresh one, okay, and messages should be the genuine messages. And the last implementation problem is that integrity of sequence number. See, here sequence numbers are sent along with the message, so there is a chance for an attacker who can freely manipulate sequence numbers, right? There may be a chance, isn't it? So he may change the sequence number, and it may cause number of problems where even though message is fresh, if sequence number is changed by an attacker, obviously the Bob will think that it is not a fresh message. So how we can solve this problem? Obviously, by following some cryptography integrity protection, by following some cryptography integrity protection, we can avoid the attacker to change this what sequence number. Okay, so that is what sequence number mechanism is all about. The next method is N1 based mechanism, the last method under this providing freshness mechanism. So N1s, that means what? Literally, you can see here, literally numbers used only once. Okay, and you can see those numbers can be a random number. So if particular number is used once, okay, then it should not be repeated. Okay, you can see for a particular one unique example is that the time of the current time. Now the time is 12 o'clock 56 seconds, right? And date is 4th November 2020. So this time will not be repeated in future, right? In the same way, we have to use such a random numbers to provide the freshness for the messages. So this is N1 based mechanism. So here the principle is that Alice and consider the same scenario. Alice and Bob wants to communicate, where Bob has to, he should treat whatever the message received from the Alice should be a fresh one. Okay, so consider the same scenario, and with respect to this method, Alice generates N1s at some stage in communication session. If communication session is started between Alice and Bob, then consider Alice will generate N1s. Okay, that means number is generated. So you can see examples for communication protocol use. Whatever protocol we use for the communication between Alice and Bob, N1 should be generated. Since Alice wants to send the message to Bob, consider Alice will generate N1. Okay, and if Alice receives a subsequent message that contains this N1s, then you can see new message is fresh. See, what I mean to say is, whatever N1s is generated here, see, whatever N1s is generated by the Alice here, okay, consider Alice will send message to the Bob along with N1s, okay. Consider Bob will send back the messages. Even he exchange message to the with the Alice, okay. If that message has this N1s, whatever she has generated here, then she will treat that message as a fresh message. That message as a fresh message. Along with the message that is received from the Bob, if it has N1s, then she will treat that message as a fresh message. Okay. And here, I have written a note here. Fresh means what? The received message must have been created after N1 was generated. That is what the freshness is all about here. Okay. In the next, 1 second. Now, with the same scenario, that is, suppose that Alice generates N1s and then send it to Bob. So along with the message, she will send it to Bob, and Bob, what he will do, he will reply back to the Alice. Then this scenario can yield 3 cases. One is that Alice cannot deduce anything from such a simple scenario. This means what? That consider Alice has received a message consisting of N1s from someone. Say, since she is communicating with Bob, she will think that whatever message received along with her N1s is the message that she is supposed to receive, right? But whatever the someone is there, here the authentication is not provided here. Even though N1s is received along with the message, here with this scenario, the someone, that means who would send a message as well as N1 is not authenticated. That means the message that is Alice has just received is sent by someone who is after Alice sent N1s to Bob. That means N1s, when Alice sent N1s to Bob, there may be a chance where attacker has taken this N1s, okay, and this N1s is sent back to the Alice along with the message. That means what? Alice will think that the message is fresh. But what actually happened here? But this is sent by someone else who is not authenticated party who is supposed to involved in the communication. That means he is not a Bob, but someone else has sent the message to the Alice. There is another case that there is a chance that the N1s could have been generated before. What does it mean? See, if we assume that N1 has been generated using a secure mechanism, as I said, N1 is a randomly generated number, right? In the previous session, we have seen pseudo-random numbers are generated by following algorithms, right? So for this algorithm, we have to first give seed value, right? If the seed value is large enough, then there is less chance of repeating the random numbers, right? So here, if the seed value is large enough, then there is a chance that N1 is not repeated, okay? So if the seed value is smaller one, then there may be a chance of repeating N1, okay? So this may be one case with respect to this scenario. And one more scenario is that since N1s was used, Bob is sure that the message from Alice is fresh. Okay. So see, with this, in this case, what happens? And as you know, N1 is just a number, isn't it? So it could be a copy. It could be a copy of a message that was sent a few days before. Okay. Since Bob was not looking over Alice, that means when she generated the N1, he gains no freshness assurance by seeing it. Okay. If Bob has freshness requirement of his own, then he should also generate N1 and request that Alice include it in a later message to him. That means what? Here, whatever N1 was used, Bob is not sure that when this N1 was generated. See, if Alice and Bob are communicating today, okay, if they are communicating today, then N1 should be generated now. I mean, when Alice wants to send the message. But Bob is not sure that N1 is generated now. It may be generated yesterday as well, right? So, but Bob will think that this is the recent N1, N1. So the message is fresh, right? So even this is a problem with respect, this is one more case with respect to this scenario, okay? So there are 3 different cases that we studied under this simple scenario. What is the first one? Here, with respect to the first one, authentication is not ensured, only freshness is ensured. With respect to second point, the N1s could have been generated before. That means since N1s are randomly generated, there may be a chance of repeating N1s. And with respect to third point or the third case, N1s was used. Alice and Bob, if they are involved in the communication, then Alice might have generated N1s before itself, before Alice and Bob start to communicate. Okay, so in that case, Bob, freshness can't be assured if it is generated before communication between the Alice. Okay, so this N1 based mechanism comes with 2 costs. That is, an entity that requires freshness needs to have access to a suitable generator, which is not the case for every application. What does it mean? So N1 should be generated. As I said, it is a random number, right? So that should have, to generate n1s, obviously we should have a suitable generator, but that will not be the case in every application. And freshness require a minimum of 2 message exchanges. So these points are very important. So freshness requires a minimum of 2 message exchanges. How it is done? See, Alice first, she will generate N1 and that will be sent to the Bob, right? That is one message exchange. And Bob, what he will do? He will send the message along with the N1s that is received from the Alice to ensure the freshness. So 2 messages are involved here. 2 message exchanges are involved with respect to N1's based mechanism. Okay. So that is all about N1's method. And here is a comparison. You can see here all 3 mechanisms are listed. Clock-based, sequence numbers, and N1. With respect to synchronization, in clock-based, yes, it is required, right? In sequence numbers also, it is required. With respect to clock, Alice and Bob should have a synchronized clock. With respect to sequence number, Alice and Bob should have a synchronized database, right? Whereas in N1 based mechanism, synchronization is not required. Communication delay, window is needed. Here also window is needed, window is needed. That means what is window is needed? See, a certain time, specific time should be defined to receive the numbers. Either it may be timestamp with respect to clock based, or it may be sequence number, or it may be N1's number. Okay. And integrity required? Yes, it is required, whereas in N1's it is not required. Minimum passes needed. Here only one message exchange is required, whereas here N1's 2 message exchanges are required. Special requirements, here clock should be there at Alice and Bob, sequence data which should be there at Alice and Bob, and random generator should be there at Alice and Bob end. So this is the comparison of freshness mechanism: clock based, sequence number, and N1 based numbers. So next, we already discussed why entity authentication is required, right? So here, in the previous class, we already discussed, see, why entity authentication is required. I already discussed all the examples, right? What is freshness, why entity authentication is required, and all that, right? And also we discussed 2 methods: biometric sign, email authentication, right? So since I've already given the introduction about entity authentication, I'll directly move to the next topic. Okay. So applications of entity authentication. So we'll see where and all we require this entity authentication. In this, I mean, with respect to your syllabus, 2 situations are given. One is access control, and the next one is as part of a more complex cryptographic process. So what is, I mean, why do we need entity authentication at access control? Because entity authentication is used to directly control access to either physical or virtual resources. Okay. And this entity, I mean, an entity sometimes, it can be a human user where you must provide assurance of their identity in real time in order to have access. For example, what? Gmail account. Consider Gmail account. Obviously, to access the Gmail account, you should provide your entity authentication, right? Username and password is required. So if you provide the proper username and password, then only you can access Gmail account or Facebook, Twitter, whatever application you want to access, right? And the next situation is that as part of a more complex cryptographic process. Here, entity authentication is a common component of more complex cryptographic process, typically instantiated by a cryptographic protocol. That means uh, while using cryptographic protocols, we need entity authentication. Like cryptographic protocols are the Kerberos, whatever you studied in the previous semester, and always point-to-point protocol, and then internet key exchange, many more, right? So whenever you use these protocols, entity authentication is also required. Okay, so where entity authentication actually required establishment at the start of a connection. I mean, Alice and Bob wants to communicate, then obviously initially this entity authentication is required. Alice should justify herself. She is an authenticated user, and also Bob should also uh, authenticate himself. He is a what Bob himself who wants to communicate with Alice. Okay, so an entity must provide assurance of their identity in real time in order for the extend protocol to complete satisfactorily. Okay, so before communication that happens between two communication parties, they should authenticate themselves. That is what this application says. Okay, and there are general categories of identification information. That means, I mean, how the claimant identify himself. I mean, how he says he is the authenticated person who can access the resource that is available in the network. Let's see those categories. So here I'm using a new word, that is claimant. Claimant is what? The person who wants to uh, prove his identity. That person we call as the claimant. For example, uh, to access Gmail account, you have to provide your username and password, right? So, being a user, the Google server has to verify username and the password. So, the Google server, you can say he is a verifier. Okay. 1 second. Okay. Uh, so something that claimant has, I mean, the claimant, how he provides identification information. The first one is dumb tokens. This dumb tokens is a physical device with limited memory that can be used to store identity information. Can you see this card where a black strip is there, right? So this actually it is dumb tokens are physical. Where is it? 1 second. Huh. Okay. See, this is dumb tokens. Am I audible? Yes. Someone please reply. Am I audible?
Yes, ma'am.
Yes, ma'am.
Okay. Okay. So dumb tokens. So if you look at this image, this is a physical device with limited memory that can be used to store identity information. So can you see this black strip here? This is the limited memory that is provided in this physical device where what identity information will be stored. Okay, so if you have a this dumb token, then a reader is required. See, if you go to shopping mall and all, if you purchase a product, obviously at the billing counter there will be a reader to read the barcode or the QR code that is there on the price tag on the product, right? In the same way, To verify the user identification information, a reader is required to extract the information that is present at this strip. Okay, so here, so this is an example using which the claimant can provide his information. Okay, so you can see in this image, it is a actually it is a plastic card with a magnetic strip, so where the what identity information will be stored. Okay, and next um, category is that smart cards. So you all are aware of the smart card, right? So where even this is also a plastic card where it contains a chip, you can see here, right, which gives a limited amount of memory and a processing power. So you can see a chip here. This will have a limited memory and a processing power. So now what is the advantage of obviously on this chip the user information will be stored. Okay, you can see here user information can be stored here. Now how it is more advantage than the dumb token, right? So here on the smart card you can store secret data more securely and can also conduct cryptographic computation. That's why the computation or the processing power is embossed on this what circuit, or you can say chip. Okay, actually for this also, for the smart card also, you required a reader. So the reader will help you to extract the data that is present in this chip. Okay, and this widely used in banking industries like debit card, credit card and all, right? So and next category is that smart token. Smart token, you might have seen this at many places. Say, for example, metro to travel, they will give you this smart token, right? So you will pay and you will get this token. So using which you will get an entry into the metro station, right? So that is another example where it will provide, which is used to store the user information. Sorry, what claimant information. So the smart tokens have their own user interface. Okay, this can be used, like for example, to enter data such as challenge number for which the smart token can calculate a cryptographic response. See, as of now, you just remember what claimant can provide his information, identity information using this smart token. So this is one way of providing user identity information for the verification, or a category using which the claimant will provide the information for the verifier to verify his identity. Okay, for this also you need a reader. Okay, you might have seen the reader in metro station, isn't it? Yeah. Yeah, that's all in this class. I hope I'm clear to everyone. If any doubts, let me know.